And then you ask, well, did it die? If yes, you're actually quite happy because then you can prove a theorem. If not, then you look for a pattern. And what does pattern mean? Well, it's usually going to look something like those sequences we were analyzing before, but it may not last forever. So you try to automatically prove the pattern by induction using something similar to what we were doing before. But the difference here is the induction is allowed to fail not just at some point in the past, but also at some point in the future. So the pattern may only last for, say, n terms or something. So if that happens, it might last forever, then you're also done. But if it only lasted, let's say, until index 5n, then you just repeat this whole slide again. But your new initial condition is the entire sequence you've looked at so far up through what you just generated. So you just keep doing this until it dies or until you can prove something. And what you actually sometimes end up with like a higher order type pattern, which you would sort of have to look at yourself to find.
So looking for the pattern is the human step, everything else?
No, this is all automated. Looking for the higher level pattern, if that comes up, is a human step, but that doesn't usually come up. The computer can do this, and it does do this. So this thing has no human steps in it a priori.
And looking for the higher pattern also will be soon.
Yes, that's something that I only realized comes up about a month ago, so I haven't programmed the computer to do that yet. So I actually did manage to sort of adapt my old methods to handle that a little bit, like specific cases. Alright, so I said assume 1 through n as your type of initial conditions. Now we're actually going to use 1 through n as our special type of initial condition. So we developed our method, now we're going to use it here. So we're going to look at the Q recurrence first with the initial conditions 1 through n. We're going to use the notation Q sub n to denote these sequences. So 2 and 3, those are just shifts of the Q sequence. So you remember invariant under shifting. The first terms were 1, 1, 2. So you just have 1, 2 now, and it works out the same way. Just that first 1 is never referenced, because we don't think it's ever referenced when computing the terms. And if you look at n equals 8, then you can see that there's actually 420 terms in that sequence. And also, if your initial condition has 11 guys, that leads to death. And also 12. The other numbers up to 13. I didn't use 1 because 1 is stupid, because then you can't compute the cube 2. But these all live for at least 30 million terms. And here's plots of the ones that live for at least 30 million terms. So here's Qn, 2 and 3. And here's 4. You can still sort of see some sort of weaviness going on here, but it's less pronounced than for the Q sequence. Again, I have no explanation for that. It just sort of happens.
Can you go back to the previous slides? I was wondering, sorry, the two different pictures. I was wondering the waviness.
It looks like it's in the same. It's nearby. It looks like this is the same number of terms.
Sorry, is that also about where the sausages happen in the other one?
Yeah, but that is the other one. This is the same. This is the Q sequence, but starting from Q of 2.
Sorry, thank you.
And then there's still a hint of it here if you look very carefully, but it's pretty much gone at this point. This is Q5. Here's Q6. It's not really there anymore. Here's Q7, Q9, Q10, Q13. But good news, if n is at least 14, it weakly dies. So how do we prove that? Well, we assume n is sufficiently large, and part of the result is going to be what does sufficiently large mean. So we start computing terms. So this is what it looks like to compute one of these. So Q of n plus 1, we plug it all in. But these guys were in our initial condition, so we know their values. And then we rewrite things. These guys were also in our initial condition, so we get 3 for Q of n plus 1. This actually assumed something. This assumed n was at least 2. The reason for that? We used Q of 2, and we assumed that its value was 2. So if n was less than 2, that would not have been okay, because this would not have been an earlier term. So that's the sort of assumption that comes up. So this is n plus 1. We can compute more of these. And I'm just going to tell you that to compute through Q of n plus 28, that requires n to be at least 13. Because we assumed, to compute, I think, this term, it uses the value of the 13th term of the sequence. So we assume that that's part of the initial condition. But 2n plus 8 versus n plus 29, this guy's bigger, as long as n's at least 21. So that means this will be the last term if we're only looking at weak death, as long as n's at least 21. But the theorem said 14, so just check the other ones. There's actually a deeper thing going on where these all die in the same sort of way, but that's a deeper theorem. This theorem you can prove by checking. So what about strong math? This is the most complicated result, and it's complicated. You'll see what I mean by complicated. Like, I'm still astounded by this result a little bit. There are parts of it that I have trouble believing are true. So now we're going to assume that n is sufficiently large, where in this case I'm just going to tell you, n's at least 118. Actually, n can usually be at least 35, but there are certain cases where 118 is required. So after those first 28 terms are the same, then you can calculate more terms, and then you get a temporary pattern between n plus 35 and 2n plus 4 other indices. And it's a period 5 pattern. And I have no idea why 5 comes up, but it does. There's one linear piece, but it doesn't have slope 1. It has slope 2n plus 4. So this is a big, think of n as a big number. So this is a very steep linear thing. And then there are 4 constant subsequences. 3 of them are small constants, but then this is a big constant. By big constant, I mean it's a constant, but it's bigger than the indices we're evaluating at. So this pattern will persist as long as this index keeps being bigger than these indices, which is why the pattern stops at 2n plus 4. Because then you don't get 0 when you evaluate this guy, you get something in the initial condition. So what happens next? Well, we have to say, well, what's n mod 5? There's 5 cases. If n is 0, 1, or 4 mod 5, the sequence strongly dies not too long after that. This is the case where you actually need the 118. For everything else, 35 suffices. So 3 mod 5, this is a plot of n equals 38, which is the smallest case where the theorem applies for 3 mod 5. This is the initial condition. This is the part up to 80, which is before the theorem starts doing things. So most of these are just described by those first 28 terms. Because 38 is not that much bigger than 28. But then you have this thing that's growing pretty fast, and then you have some stuff that looks kind of linear down here, but there's some noise. And these are actually infinitely many 4s, or at least we think it looks like it might be infinitely many. But every 5th term is 4, as far as we can compute. So Rachel, getting back to your comment, this is sort of like interleaving. Some of the sequences look random, and some of them are well behaved. So every 5th term is 4, but the rest are not well behaved. I can describe them in terms of each other, but aside from that, don't know. How about 2 mod 5? So this is the pattern we had before. So if n is 2 mod 5, we actually get another thing that looks like that, starting just a little bit after that and going till about the square of that. So it lasts a lot longer. And then we have to look at cases about n mod 25. And it might keep going. So a technical description of what goes on. We define sequences like this. These are the initial values of those sequences. And they're described by these recurrences. So the A's are described in terms of the previous 2. The B's are just the successive differences of the A's. And then starting from I equals 1, this is the pattern you get. So if n was 2 mod 5, this is the next pattern, where it's A1 plus 7 through A2. This pattern happens. And then once you get to index A2, you check this value. And then there are 5 possibilities as you're looking at it, mod 5. The 0, 3, and 4 cases correspond to the 1, 4, and 0 cases before, and it dies in exactly the same way that those died before. If this is 2, you get, it's like that n equals 38 sequence. You start having 4s interleaved with chaos. If you get 1, increment I and do this slide again. So here's Q42. Rats, you can't really see much here. But this is going to be that chaos thing, and this one line is actually just one of those parts. Because remember, each one's about the square of the length of the previous. So to see that more clearly, here's the same sequence. Both axes are now logarithmic. This is the initial condition. This is before it's strong. This is before it weakly dies. And then you can literally see 1, 2, 3 of those period 5 patterns. And then these are 4s, and that's the chaos. So we can actually sort of describe this by a tree. So those two descriptions, it's not necessarily clear just from those descriptions that that second thing ends up depending on higher and higher powers of 5, but it's not too hard to prove from that. So what you can do is you can write n in base 5 and start reading the digits from right to left, and this tree will tell you what the behavior is. So 42 in base 5 is 132. So that's this leaf right here. So 132 ends in 2, so you start here. And a black node is an internal node, and that means you have to go deeper down the tree to figure out what happens. And in the meanwhile, you get another of those period 5 things. So then you drop down, you're at 3-2. Another internal node, so you get another one. So that's why we had 1, 2, 3 of those patterns. And then you get to 1, 3, 2, and that's yellow. So that's this 4s and chaos type thing. So hopefully right now you're looking at this tree and looking for a pattern. At least that's what I did. And you see, oh, there's one node of every color at every level, but it's not really clear which one's going to be which color. Maybe you see something that I didn't see, but you see something?
Is the tree cut off? There's a black.
No, there's a black node here. There are children below this one.
Okay.
So this is not the entire tree. So of course I just generated more of it, and what? Oh. I did not believe this when this happened, but I have confirmed that it happened. But you can't generate these. You for sure cannot generate these, because the number of terms before this actually happens is ridiculous. If you start with about 3,000 and then square it 6 times, and that's when this would start happening. But you can do some sort of symbolic tricks to sort of shortcut a lot of that, because in the interim the sequence is very regular. There's not a lot of entropy here. So then you can do more levels, and now the things happen. And then, so level 6 is all black, level 11 is also all black, and level 16 is also all black. I can't compute down to level 21 because it's too big. I actually wouldn't be that surprised if this tree ends up being finite. Like at some level you have all your black children have non-black children, and then the tree would be finite. I don't know.
Sorry, at this stage it looks like all the things have monotone children. Is that the case?
Yeah, after level 5, everything has the same color tone. I haven't been able to prove that, but it's probably not that bad to prove. But. And then also after level 11, things have monotone grandchildren. So it's weird. So, all right. Yeah. So, that like you said, the word monotone. Yeah, monochromatic. All right, so how about this 3-term recurrence? So this is that recurrence that we saw that slow solution to earlier. So this theorem is going to, in some sense, be more complicated than the previous, but in another sense, it's simpler because there's no crazy tree. So if n is at least 74, there's a period 7 pattern in place of that first period 5 pattern. And then there are 7 possibilities, depending on n mod 7. All of them lead to strong death after not too many more terms. But you'll notice that some of these numbers are kind of big. And these are all tight. So like 3, 2, 4, 7, 1 doesn't work. This theorem does not apply to it. So here's the sequence through 3, 2, 4, 7, 8. This is just the period 7 pattern, so you can see what that looks like. You're probably wondering why there's only 6 lines. That's because 2 of the pattern pieces are the same. So then you generate more terms, and you can see that there is some sort of regularity in the terms before it dies. But then it dies, and some of the terms get huge. So this is a log plot of the same sequence. So yeah, that previous theorem covers all but just over 6,000 n values. So what can we say about those sporadic n values? So 5 and 6 were that slow sequence from earlier, so those don't even weakly die. 7, 8, 9, those are sort of like the Q sequence, we don't know. And if n is at least 14, we know that we have an analog to that weak death theorem for the Hofstadter sequence. So you get after n plus 24 terms, it weakly dies. These values, for anything in this set, it weakly dies but does not strongly die. For things in that set, it weakly dies, and we don't know if it strongly dies, but it probably doesn't. So those again sort of like the Hofstadter sequence. And any other n value, it strongly dies. But, fun fact, if n equals 20,830, it strongly dies, but it takes a lot of terms before it strongly dies. And this is because there are some giant constants that start appearing that sort of dominate the behavior, and you have to wait till those constants become small before anything interesting happens. So you get a sort of period 16 thing, but the problem is that period 16 thing has parts that grow exponentially. And then after that, one of those exponential growth terms becomes the constant in another one of those. And then it dies. So these are all but 2 of those values from that set that doesn't strongly die. These ones eventually just start alternating with 2s and things times powers of 2. I don't think that's that interesting. It's just sort of like, instead of getting a 0 and causing death, you got a 2 late in the sequence. So these are kind of boring, but they do not strongly die. But 193 and 340, so 334, 42, those are more interesting. These are built out of period 5 sub-patterns that each one is 6 times longer than the previous. And the transitions are all the same between them. So these ones sort of have a fractal structure that's really interesting. So here's a graph of the first 40,000 terms for 193. You can see sort of 2 of those things. There's actually a third one sort of lurking down there. But there's this one, and then there's this one, and those meet eventually, and then you have the same sort of transitional pattern. And it's pretty easily seen on a log-by-log plot of sort of what's going on. This is the first 200,000 terms, and the log is base 6, which is why these things are 1 apart. And you can also look at...
vertical lines actually stop, or do they keep going?
Everything keeps going. Or which lines?
The vertical ones.
The vertical ones, these?
Yeah.
These are a finite number of transitional values. Like, I don't remember how many it was for this sequence. I want to say it's like 441 of them. And it's the same pattern every time.
The third from the right seems to go above the diagonal.
Yeah, I think this is where the pattern actually starts. Either that or this value, the values are small enough that you can see more detail. I'm not sure which it is. All right. So I basically got like 1 minute left. Do you mind if I take a little bit extra, or should I just go through things really quick? All right, so I'll just show the rest of the pictures I have. So 4-term recurrence, if you just add more terms, you just get really weird behavior. So it starts out with some linear stuff, and then it goes nuts. 5 terms, 6 terms, so you have that same sort of linear thing at the start. 7 terms is different. I don't know why. And then here's more with 4 terms, 7 terms, 7 terms. Right, and then I had these other initial conditions I looked at, which are alternations between n's and even numbers, because if you start with that, it continues through index n. But you can look at other things too. And in this case, they're mostly easy to describe, but there are some other things that happen depending on mod 4 or mod 12. So here's n equals 5, which is another pattern, sort of like that 193 type thing. Here's a log plot, so you can see what the transitions look like. Here's a log-log plot, so you can see in between. Here's 41. There's actually 2 different types of transitions here. 57 is that staircase sequence from earlier. This is one of those with like a higher order type pattern. 89 looks like you took the 57 example and butchered it. That's the whole sequence. 91, that's an entire sequence. And then the 4s, there's a weird case involving something not being 4 times a triangular number. That is important. And so a nice multiple of 4 is 216. So this is the entire sequence for 216. A nice number that's 2 mod 4 is 722. So here's the solution for 722. This is the whole sequence. Here's a log plot of that whole sequence. Each of those polynomials is 1 degree higher than the previous. And then here's 312, which is 4 times a triangular number. That is that waterfall sequence, and here's the log of it. And then 4n is some sort of similar stuff. 311 is a nice number that's 3 mod 4, sorry. 3 mod 4, and you get, that's the whole sequence. 922 is a nice number that's 2 mod 4, and this is somewhere in between the levels of 312 and some of the other things we've had. And here's a log plot of that. So we've got a whole diversity of things here, but I just scratched the surface. There's a huge treasure trove lurking beneath the surface here that lots more of these initial conditions to be studied. Thank you.
This is the public part of the talk. Thanks for coming on the committee. Now, if you have questions, you can ask Mr. Fox after, even if he stays now. You can answer. Hopefully, we can talk. We don't know yet.